Hello everybody, welcome to another MCAT ACE lecture, and in today's lecture we are going to discuss chirality and stereoisomers. So as a lead off to this lecture, I just want to state the context of discussing stereoisomers and chirality here is primarily going to be in that of an undergraduate organic chemistry course. So when we start looking at this, we're really going to talk about R and S configurations. We're going to talk about the ranking rules, and we will also discuss the idea of enantiomers, diastereomers, meso compounds, and we will relate it to some biochemistry in the importance of drug design. So we'll discuss briefly a case study where a drug known as thalidomide was sort of banned from the market because of some of the side effects, because they were not paying attention to what's known as racemic mixtures, or administering different stereoisomers of the drug. So you can see an outline of what we're going to talk about here. I'm not going to cover or discuss in great detail D or L. So a lot of people also know stereoisomers when we talk about the D or L configurations of whether it be carbohydrates, amino acids, things like that. That gets into a biochemistry discussion that is still relevant here, especially when we talk about absolute configuration and relating RS back to R and L. However, when we, or I'm sorry, D and L, but when we discuss this, we're really going to focus it for the sake of time, because we're condensing this lecture into about an hour or so. We're going to focus on chirality in relation to stereoisomers for organic chemistry. All right, now, to take a look at this, we are going to start by going through some definitions. Especially for chirality, there's a lot of terminology we want to nail down as we're getting ready to sort of throw this out and talk about it here. So we're going to define chirality and stereoisomers, some of the specific stereoisomers, and we will talk about non-superimposable molecules. So you keep hearing this term thrown around, mirror images or non-superimposable images. So we'll talk about what that means. We will talk about determining R and S orientation. So many students know this as the ranking system. The formal name is the Cahn-Ingold-Prelog ranking rules, which is where you take a periodic table, and I would suggest that you have one as we walk through this, like most lectures, and you go through and you find which atom has the higher atomic number. That one gets ranked for priority. And so then we do our 1, 2, 3. We keep priority 4 facing away from us, and we determine whether we have an R or an S orientation, which is really clockwise or counterclockwise respectively. So we'll take a look at that. We'll also discuss in these rankings how to deal with double and triple bonds. So a lot of students, it's easy for them to say, well, oxygen comes before carbon, so therefore I'm going to rank this alcohol as a higher priority than, for instance, this methylene group, a CH2. But a lot of students run into trouble when they start seeing, for instance, carbonyls. How do I deal with a C double bond O when I'm ranking that versus just an alcohol, which would be a C with an O, a single bonded O attached to it. So we'll deal with double and triple bonds. We'll show some examples with that. We're then going to discuss meso compounds briefly. Meso compounds tends to be an area where students will struggle because you're looking for planes of symmetry within the compound itself. So some compounds can have what's known as stereogenic centers or chiral centers, but overall the molecule is achiral, and that is known as a meso compound, where you basically have internal stereocenters that are canceling one another out due to the plane of symmetry. And how do we actually categorize whether something is canceling out like that? It's the ability to rotate plane polarized light. So we'll have a brief discussion here about these molecules and what they could do with plane polarized light. The fact that R and S are opposites, so however much light your R enantiomer will rotate, the S will rotate it an equal amount in the opposite direction. Another point of confusion there, a lot of students think that R will always rotate light to the right, like dextrorotatory, and S will always rotate it to the left, like levorotatory, because of the clockwise, counterclockwise. That's not always true. So you can have R absolute configurations that are paired with either the D or the L. You have to determine it experimentally. And this is one of the ways you can do that with plane polarized light, if you can isolate one of the two enantiomers. All right, and then we will discuss certainly the importance in drug design, especially because you guys are going into MCAT and you have hopes of med school and becoming a doctor. It is very important to understand medication from this perspective. This is something that is implemented by the FDA. You have to do very rigorous testing if you are going to attempt to administer a drug as what's known as a racemic mixture. So let's say that the drug has one stereocenter. Am I going to administer the R version or the S version of the drug? Well, a lot of times companies, it can be very expensive to sort that out, so they want to administer it just as a cocktail where they give the R and the S. And that's fine, but they have to prove by separating them out and testing each enantiomer separately that neither one is going to cause serious side effects or issues before they're allowed to put it together and package it as one whole piece. Otherwise, if you have to separate it, it can get very expensive to go through that process, because most reactions somewhere along the way are going to deliver these racemic mixtures. You're going to get a mixture of stereoisomers. It's very difficult to separate them out because they share the same physical and chemical properties. All right, so that's really the overview of what we're going to do. We will certainly have our summary and our review questions at the end of this. So let's go ahead and dive in and get started. So we're going to discuss some terms first, and I wanted to bring some of these up so that we can walk through them together. So what does it mean to be chiral? Because we're going to hear this term thrown out a lot. We're going to say a molecule is chiral, a molecule is achiral, and we may even talk about specific atoms within the molecule being chiral. And you can see the definition below this is chiral center. All right. Now, what does it mean to be chiral? The real definition of chiral or chirality is when you have molecules that are going to be non-superimposable, or they cannot be superimposed on top of one another, right? So in other words, the molecules have to be mirror images of one another, at least to some extent, okay? Now, we can argue when we get to enantiomers and diastereomers to what extent they are mirror images of one another. But the general rule here is that if you can rotate a molecule and superimpose itself on top of itself, then you have the same molecule. So it's not even a stereoisomer. We wouldn't talk about, is it a diastereomer, an enantiomer? It is just the same molecule, okay? And you have to check for this because a lot of times you can rotate a molecule in a different format, and if you're good at visualizing it in 3D, you're going to be able to rotate it and realize that they line up perfectly with one another. It's the same exact molecule being viewed from a different angle. And I will tell you from years of teaching and experience, this takes practice. You usually want to sit down with a model kit. Now, certainly when you're taking the MCAT, you're not going to have that advantage, but it will help you from a visuospatial perspective to deal with this, all right? Most students, this is one of the most difficult concepts for them to grasp when they're first going through Organic 1, and that is because you're used to doing a lot of these reactions. You're used to being able to memorize, right? A lot of the MCAT, we talk about memorization and, little tricks for mnemonics. Stereochemistry can get very difficult to do that because you cannot memorize all of the different rotations or designations for a molecule. You have to really be able to see it in your mind, especially when you don't have the model kit available. So I would suggest spending some time and practicing this with a model kit if you have one available. All right, now, when we talk about being superimposable, what does that mean? It means I could drag something over top of its image and it would be a perfect alignment. So do this as an exercise real quick. This is what I do with my students in class. Take your hands and look at your hands with the inner palms facing you right now, all right? If you drag your hands over top of one another, you're going to find that these cannot be superimposed on one another, all right? And that is because if you take a look, right, your thumbs are on opposite sides, and then your fingers are misaligned. So you have the pinky where the main pointer finger is, right? Then your ring finger on top is over top of your middle finger on the backhand. And so it's a complete misalignment. Now what I want you to do is take your hands and have them facing one another, all right, as if you're about to clap. And so if you take a look at that, you can see they are mirror images of one another. And this is what we're talking about with molecules. The hands are a very common example we use as organic chemists when we're trying to describe this. So if you look at your hands in front of yourself, if you're about to clap, they're a complete mirror image. It's as if one hand was standing or sitting right in front of the mirror and it's seeing its reflection back, right? And so that is what it means to be non-superimposable. It's a mirror image, but when you attempt to take the hands facing the same direction, you can't have one that's palm up and the other that's palm down, because then they look like they are completely superimposable. But if you look at them the way that they are both palm up in the same sort of orientation and you attempt to drag them over top, they are non-superimposable. And that's what we're talking about from a molecule perspective. All right. Now, what is a chiral center? Again, I'm framing this talk because it can get very wide in the context of organic chemistry. And a chiral center is going to be a carbon with 4 different groups bonded to that carbon atom. This is also known as a stereocenter, or sometimes you will hear the term stereogenic center. And all of this is referring to basically a carbon that's got 4 different unique groups that are bonded to that carbon. Now, when we talk about this, you have to have chiral centers in order for a molecule to be chiral overall. Now, just because you have a chiral center does not guarantee that the molecule will be chiral overall, because like I said, you could have planes of symmetry within a molecule, and we'll take a look at that as we practice and we look at all of this material over the next hour or so. All right. Now, what does it mean for a carbon to have 4 different groups? Well, it means that group 1 is not the same as group 2, and I'm going to show a little bit of stereochemistry here since the subject is involved. 3 and 4. All of these groups, 1 cannot equal 2, cannot equal 3, cannot equal 4. That's what we're talking about here. So for instance, and this is a very important sort of shortcut when you're determining these chiral centers, no CH2 could ever be a chiral center. And that's because by definition, the CH2 has 2 hydrogen groups associated with it. It doesn't matter where they appear. If they're on the wedge, the dash, one of the bonds that are within the plane that you're looking at, okay, it doesn't matter because the 2 hydrogen groups are symmetrical. They're identical to one another. And so what we're going to find is that when we talk about chirality, symmetry, or actually asymmetry, the lack of symmetry, is very important for determining chirality. Because when we have symmetry or planes of symmetry, we are not going to have chirality occurring, whether it's at a specific atom or whether it is for a molecule overall. All right, so this certainly follows that then a CH3 could not be chiral. A CH could be chiral because H would just be one atom, but it depends on what the other atoms are, right? So for instance, if I had a CH group and it was like an isopropyl where there would be 2 CH3s, well then that could no longer be chiral because a CH3 is the same thing as another CH3, and so this could not be chiral, right? However, some CH groups, let's say that I have a carbon that's got a hydrogen, it's also got a fluorine. We'll just use halogens for this example. It also has a chlorine, and it also has a bromine. Well, now this carbon suddenly has 4 unique groups, right? Hydrogen is not the same as chlorine, is not the same as bromine, is not the same as fluorine. So this does meet the definition of chiral center, or a stereogenic center, and this carbon could be marked as such. And if this was the entire molecule, then we could say that this molecule is chiral, and therefore we could start talking about stereoisomers, which is what we're going to get to. All right, now one of the other ones that you can automatically rank out, and you will not ever count as a stereocenter, is anything involved in a double or triple bond. So for instance, a carbonyl, okay, C double bond O, is not going to be considered chiral, at least not in a tetrahedral sense. There are subjects where you can start talking about sp2 planar molecules and what type of, which way you're approaching the face of the molecule and prochirality. That's an upper level subject. We're not talking about that here. So what we're really looking at here is the fact that this carbon, it could be bonded to 2 other things here, and even if those 2 things are different, the fact that this carbonyl exists, it means that carbon is bonded to the same oxygen 2 times, and that violates the 4 different groups that we're looking for. All right, so CH2s, CH3s, and any carbon that is involved in a double bond or a triple bond. Now, many students will ask me, can you have, for instance, nitrogen or oxygens or anything like that where they could be chiral? And the answer is absolutely. You can have chiral centers that aren't focused on carbon, but most of the time especially in the context of organic chemistry, and that's what we're studying for the MCAT, it's going to come up relative to carbon. And that's especially true because carbon has the ability to form 4 unique single bonds. And that's not to say that a nitrogen couldn't, right? Because we could have a nitrogen that's going to have 4 unique bonds. If it doesn't have the lone pair, it would have a plus charge here. But I could certainly have 4 different atoms there making that nitrogen chiral. So it's not unique to carbon, but carbon tends to be an atom that will be able to become chiral more often than not when we look at some of the others. Oxygen very often needs 2 lone pairs associated with it. You can get away with 1 lone pair, but then you would need 3 unique groups around the oxygen. So it tends to be less common with some of the other atoms. All right, a molecule will not be chiral if a plane of symmetry exists. Now we've talked about this, all right? So this means that some molecules can have chiral centers, but overall the molecule can be chiral. I'm sorry, that should be achiral. Okay, there we go. Sorry about that. The autocorrect kept trying to change it to chiral. So the term achiral is simply the opposite of chiral, okay? So chiral centers may exist. You may have individual carbons that are chiral centers. However, the molecule, when you take a look at it, is going to be achiral. So for instance, let's say that I have a 5-membered ring like this, and I have on this side a chlorine that looks like this, and on this side I also have a chlorine right here that looks like this. Well, if I take a look at this, right, there would be hydrogens implied behind, and so each of these would be considered or designated as chiral centers. So if you take a look at it, and we will certainly get further into this with more practice, I've got a chlorine, I've got a hydrogen. Now here I have a CH2 and here I have a CH2, but then when I branch one more step out, here I have this carbon with the chlorine group, and here I just have another CH2. So these do differ as I'm starting to walk along those last 2 substituents, and I can see that this one right here on top is different using the chlorine versus just another CH2 on the bottom. Okay, now the opposite would be true if I came over and I started ranking this chiral center right here. I would find that it goes the same way. Now we're not going to worry about designating this as R or S yet because we haven't gotten that far along. But what you should be able to see here, I'm going to redraw the molecule, is that there is a plane of symmetry that runs through the molecule. So I could draw a plane of symmetry directly through this molecule right here, and almost like a piece of paper, I could fold it up and I would find a mirror image within the molecule. And so what's interesting here is that I will have chiral centers. I certainly have a chiral center here and a chiral center here, right, with these 2 carbons. However, the overall molecule is achiral. This term is known as meso, which is when you have chiral centers present, but the overall molecule will be achiral. So remember, as we were talking above, we said that it's not a guarantee. You're not always going to end up with chirality just because you have chiral centers, but it is a prerequisite for chirality. All right, now these terms here. We have enantiomers and diastereomers. A lot of students will mispronounce the second one as disastomers. It is not disastomers, it is diastereomers. Now, enantiomers are going to be perfect non-superimposable images, just like the hands. So a set of stereoisomers that are non-superimposable at every single chiral center will be considered a set of enantiomers. Okay, so that means every single chiral center that is ranked as R or S, it will be ranked as the opposite orientation when you look at the mirror image. That would be a set of enantiomers. Now, a diastereomer is a little bit more complex. It's going to be a set of stereoisomers that are non-superimposable at 1 or more chiral centers. You at least have to have 1, otherwise it's the same molecule, but not at all chiral centers, because if they were changed in their orientation at every chiral center, we climb back up to the definition of enantiomer. All right, so what does this mean? I'm going to draw a relatively simple example, okay, to help explain this. So let's say that I have some chained carbon group here, right? And I'm not going to draw out all the substituents, but let's just say that this right here, and this right here all are determined to be chiral centers, right? So when we take a look at this, let's say that we rank these and we find that it's R, S, R. That means the enantiomer of the compound shown above would have to be the S orientation here, the R orientation in the middle, and the S orientation back at the top again. All right, so that would be an enantiomer because at every single stereo center, at every chiral center, they're differing in their orientation. The R's become S's, the S's become R's. That's the definition there. The diastereomers, now this is all relative to this compound that I'm highlighting, because as soon as I pick out a different compound, then I can talk about different sets of enantiomers or diastereomers. Okay, so right here, this would be the enantiomer of the original compound. Now in the green color, we're going to draw the diastereomers. Okay, so the diastereomers, if I were to take a look, I have to differ at least one. So if I started with an R, we'll make this an S. I don't have to differ at the others, so we'll keep this one as an S, and we will keep this one as an R. So we're only going to differ at one stereo center here. We'll keep two of them the same. This would be ranked as a diastereomer relative to the original compound we highlighted in purple. Okay, so then I could do another one where I change just one more. So let's say that this one is now R, and this one, which was S, has become R, and then we keep this one as R. This is another example of a diastereomer, right? And then let's say that I have another one, right? Because I could keep going with this. Let's change two of them this time. So in this case, I'm going to say, all right, this one can remain as R, but then the others will change. So this one becomes R, and this one becomes S. That would be another diastereomer relative to this initial compound. All right, so I think you get the point here, is that if I can superimpose at one or more, so it could be two, but if I did all three, then that's the enantiomer again, right? And every compound will have its own enantiomer. So while this compound that I'm going to highlight in green down here is going to be a diastereomer to the original purple one that we had here, I could also draw the enantiomer of this diastereomer, right, by drawing out the compound. And I could say, all right, well then I need R right here, and right here, because that was S, I need R. And then the top one there would need to be S, okay? I didn't even realize, but I drew that over here. So this guy right here, okay, these two would be enantiomers to one another. So every molecule will have its own enantiomer if it has chiral centers, and then you can also have sets of diastereomers. And you can see that the sets of diastereomers are really only going to be limited by the number of chiral centers that you can play with and change the R or S orientation. So the more chiral centers I have, the more diastereomers that are possible. All right. Now, to sort of wrap up the definitions here so we can get started on ranking R or S, let's talk about this. A set of enantiomers only contains two molecules, so every set of enantiomers consists of one perfectly non-superimposable molecule with another. All right. However, the diastereomers of that set can contain many stereoisomers. So the only time you could not have diastereomers would be if you only have one chiral center, right? So for instance, if I drew out a molecule and I said that this was a chiral center that had the designation R, it's only got one other possibility, right? Which is that this could be S. And so these would be enantiomers of one another. I couldn't get any diastereomers out of that because I have to change just the R, the S. And if I say, well, what if I keep this as R? This is not a diastereomer. This is now the same compound, right? So that's the same compound that I just showed above. There are no possibilities for diastereomers when you only have one chiral center. However, as soon as I pick up two chiral centers, now I can start changing one chiral center and leaving the other one in the same orientation. Now I can invite diastereomers into the stereoisomer family while I'm working with that. All right, so finally there is a calculation here that's known as the stereoisomer calculation for when you're dealing with R and S. and it states that 2 to the n, where n is the number of chiral centers, will be the number of stereoisomers. So for instance, if we look at that example I had above, I had a total of 3 different stereoisomers. I'm sorry, centers. So what could I get if I had 2 to the n? Well, that would be 2 to the 3, which would mean that I could get a total of 18. Now this will escalate quickly as we add that, because if I had 4 stereocenters, right, now all of a sudden I can do 16, and if I have 5, I could do 32, and so on and so forth, right? 64, I can keep escalating based on the number of stereocenters that I put in there. So if I take a look at this, let's look at the example with 3, right? So if I had 3 stereocenters, what are the possible orientations they could have? Well, they could have R, R, R. They could all be R, right? Or they could all be S. So that's 2 of the possibilities. Now we want to get to a total of 8 to prove this to ourselves. So we could also have R, S, S. That would be 3. We could have R, S, R. That would be 4. We could have R, R, S. That would be 5. We could have S, R, R. That would be 6. We could have S, S, R. That would be 7, right? And squeeze a little room here for the last one. So the last one, I have to look here, would be S, R, S, I believe. S, R, S would be the last one. Okay? So those are all the possibilities. You can see some of them have 2 S's, some of them have 2 R's, some of them have all 3 R's or S's, but this would be the grouping of possibilities as far as, you know, and we're assuming that this is stereocenter 1, 2, and 3 as we go along here, right? And we have the different varieties. So here's 1, 2, and 3. So that's 8. So you could see how fast this is going to explode, because if I add just another stereocenter, I all of a sudden am going to exponentially increase the options that are available as I climb each time in that exponent, right? So it's going to go from 2 to 3 to 4. As I'm climbing up in that number that I put there, I'm going from 4 to 8 to 16 to 32 and so on and so forth. So that is how you can determine this. And again, if you pick out any 2 of these, you'll be able to find a set of enantiomers. So let's just take those 2, which means that in comparison to the RRR, all of these others are going to be diastereomers. All right. So hopefully this is clear. We really want to move on to designating RS at this point since we've talked about it. So I'm going to clear the board of the definitions and the discussion, and we will move on to R and S. Hopefully everybody has a good understanding of enantiomers and diastereomers at this point. Okay, everybody, so what I have done is pulled up the ranking for R or S when we get ready to start talking about chiral centers and how we rank them. So again, if we scroll back up to the summary, we're really looking at this portion here where we're talking about determining the R or S orientation. The first thing we're going to go over are the Cahn-Ingold-Prelog ranking rules. And then we will talk about whether we assign R or S based on that. So if we come down here for ranking R or S, there's really 5 general steps you want to follow, and if you follow these steps, you should be able to rank a compound or a chiral center as either being R or S. And then you go through, you rank all of your chiral centers and their orientation is R or S, and then you can find out the configurations and start playing around with enantiomers and diastereomers. So the set of rules for ranking this, the first one is that you're going to rank based on atomic number of the immediate atom that is connected, and the higher atomic number is going to win in a case like this. So for instance, if I have a carbon and then I have 4 different groups attached to this carbon. All right, so let's say that I have something like this, and we'll say that I have hydrogen here, I have a CH3 here, I have, I want to keep all of these different, so I have a chlorine here and I have an OH here. This is a good example. All right, so what if I have a compound like this? Well, here is the potential chiral center, right? So this is what we're going to be looking at. So some of these are easier than others, and you're going to see as we go down this list, the complexity is going to increase. So when we first take a look here, all right, what I would say is what is directly connected to the carbon, to the chiral center itself that's in question? Well, I've got a hydrogen. What's connected at the top here? So when you say a CH3, it's really the carbon that is connected, not the hydrogens. So the carbon is what we're going to use in our ranking here. Then I've got a chlorine, and then here I have an OH group. This alcohol would serve as an oxygen, being the first ranking member. So this is very important because some students will get confused, especially as you have carbons that have other carbons attached to them and the complexity starts to increase. You need to keep in mind it is the immediate atom that is connected to the chiral center that gets ranked. So in this case, it's HC, Cl, and O. That's a very clear-cut example. So when I would rank these, I would say that chlorine is going to be ranked as number 1, right? And then out of these, oxygen would be ranked as number 2. That one would be the next winner. Then carbon would be number 3, and then hydrogen would finally be number 4. So whenever you have a hydrogen, and many times you're going to find hydrogens will always be ranked as the lowest possible because they're at the beginning of the periodic table. They have the lowest atomic number on the periodic table. So therefore, anytime you see an individualized hydrogen, that's always the lowest group. You're going to put it in back when we get to that point as quickly as possible, okay? Because you want to orient this so that it's going to be facing the user. In this case, it already is in back of the plane. So when I say in back of, keep in mind that the way we're looking at this is these two groups are in the plane, and the plane is meaning the dimension that I'm looking at as I view onwards. The wedge is going to be out in front. So this is out in front of the user or the viewer, and then this dash part represents what would be in back. Okay, so imagine that you have a plane in front of you, a flat surface. You can think of it as a chalkboard or a large screen TV or anything like that, all right? So what I'm saying is that two of these groups, the ones that don't show the wedges or the dashes, are within the plane. So take your plane that's in front of you. You've got one of them going straight up in the plane, the other one is coming sort of down but in the plane, okay? And then, coming out of that plane, the wedge is what's going to be coming out in front of you. The dash is going to be what's behind you or behind that plane. So if you imagine you have your whiteboard or chalkboard, you've got one group coming out in front of the whiteboard or chalkboard, two of them that are within that whiteboard or chalkboard, and then one that is behind it, almost as if it's going into the wall that you're facing. Okay, now the goal is going to be to always get that fourth group behind you, facing away, because when we rank R or S, we're going to do clockwise or counterclockwise. But if you think of, for instance, a clock, right? So here's 12 o'clock, here's 3 o'clock, here's 6 o'clock, and here's 9 o'clock. When you're facing it, right, this is clockwise, but what happens if you took the face of the clock and turned it the complete opposite direction from you? Well, at that point, the 3 that's here would be flipped to where the 9 is, and the 9 that's here would be flipped to where the 3 is. So again, mirror imaging sort of behavior. You have to keep in mind if the lowest group is in front of you, then when you're assigning R or S, it's going to be the opposite of what you're seeing. All right, so we'll get to that and we'll look at some examples. All right, now, number 2, what happens if I hit a tie? So the example above, there was no tie, right, in the potential for which one was going to be higher in the ranking. But sometimes you come across ties. So for instance, what if I had a stereo center that looked like this? I'm going to change up the color here again. All right, so what happens if I have a carbon, and this carbon has, we're going to keep the lowest group in back for now just to make it simple, okay? But let's say that it has a CH2OH, it has a CH2CH3, okay? And then out in front, it's got, we'll say, an amine group, right? An NH2. So in this example, we have to look at it. Is this carbon a potential candidate for a chiral center? Yes, it is, because it's very clear that there are 4 distinct portions that are coming out of this carbon that are not the same. So let's knock out the easy ones. Hydrogen, always number 4. Okay, now this nitrogen, take a look at what's attached. It's a nitrogen. Right here, it's a carbon that would be directly attached. So carbon, and right here, it's a carbon that would be directly attached. So carbon, carbon, nitrogen. Nitrogen is higher on the periodic table, so the amine here is number 1 in its ranking, whereas the hydrogen is 4. So those are the two easier ones, right? So as we go along here, I see a CH2 and a CH3, a CH2 and an OH. So the way that you do this is you want to look at what is the immediate connected atom. So for ties, you're going to rank the connected atoms, and if it's still tied, you're going to continue until there's a clear difference, right? So in this case, let's take a look at the carbon at the top. The carbon at the top is going to have an H, right? An H, because it's a CH2, and then an O, and that's part of the OH there. Now this is what's connected to the stereo center right here, right? So that's our ranking. It's going to be H, H, O. And this will be important when you want to do tiebreakers, because you're going to look at the sum of all the atomic numbers and see which one is going to outrank the other. So then I look at the other CH2, all right? So let's change the color just so we're keeping track of this here. Okay, so now we're talking about this CH2 right here. That CH2 is going to be an H, because it's a CH2, another H, and then it will be attached to a carbon, and that's based on the CH3, right, that's coming off here. So in this case, it would be hydrogen, hydrogen, carbon. Well, which group is higher ranking, HHO or HHC? And the answer is the HHO is going to be higher ranking, all right? And so that means that this group up here is going to get rank 2, and then this group here is going to get rank 3. And so that is how I would go about ranking those when I have the same identical atom. Now this may seem obvious still at this point, because you say, well, of course, I've got an OH here and I've got a methyl group here. So it's quite obvious that one is, going to supersede the other as far as the ranking. But that's not always going to be the case. So let me clear it off here. Okay, and it may not always be quite as evident to you. It may be if you're good with your visual skills. But let's say that I've got an example where I have a ring like this. Okay. And so then I say I've got up here a methyl group, right? I've got a hydrogen that's coming off here, and then I've got a chlorine right here. So the question is, would this be a stereocenter, right? And the answer is yes, it would, because here it's a CH2, here it's a CH2, right? And then here it's a CH2, where here it is going to be a C with an H, another C, and a Cl, right? Whereas this one right here is going to be a C with an H, and another C because of this carbon at the bottom here. So H, carbon, and Cl versus H, and carbon, then this entire side is going to be ranked as number 1 in this case. Okay. Now, why is the methyl not number 1? Because this is C, H, right? So there's 3 H's there, whereas these CH2s, and I know it's getting crowded here, but these CH2s are attached to another carbon instead of just an H. Okay? So it can get a little more complex when you have ring systems like this, and this is important because it says continue until there is a clear difference. Sometimes with ring systems, there's not going to be a clear difference and you're going to converge on the same spot. So if I had moved that chlorine to the bottom, so in other words, if I had taken this chlorine and I moved it here instead, now all of a sudden I don't have a point of differentiation. So I can say I have a CH3, I have an H, but look at this, CH2, 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 they both converge at the same time on this carbon down here. And so at that point, this can no longer be counted as a chiral center. That's out of the running because of the symmetry. Remember we mentioned symmetry at the beginning. This molecule has some level of symmetry to it, and that's making it achiral. This would not be a chiral center in this case. All right, so that is the idea behind Rule 2, when you need to continue branching, and it'll happen fairly often where you have to continue branching until you can actually determine it. All right, so then double bonds are counted 2 times in their ranking, triple bonds are counted 3 times. So what does this mean? This means that if I have a carbon, all right, let's say that I've got something like this. I've got a CH2OH, and I've got a C double bond OH. So I've got an aldehyde here, and then you can pick out two other groupings, right? So let's say I just have the H and I have a CH3, right? So H is going to be number 4. CH3 would be number 3 in this case, because this is going to be a carbon that is attached to a hydrogen, and an oxygen, right? But now the question is, what happens when we get to this carbon? So do I count this oxygen once or twice? And the rule that's set out is that this will get counted as 2 individual oxygen bonds for ranking purposes. Now this is certainly not the actual makeup of the bonds. This is a double bond. We don't have 2 individual oxygens here. But for the sake of ranking, we count this as 2 oxygens. And if I had a triple bond, like let's say I had a C triple bond end, a nitrile, then that would count as something that looks like this in its ranking. Okay? And that's how we help with some of these tiebreakers. So in this case, I have a hydrogen, and an oxygen, where in this case I have a hydrogen, an oxygen, and an oxygen. So that means that the aldehyde grouping is going to be rank 1, and the alcohol grouping is going to be rank 2 here when I'm looking at it. All right, so that is how we end up dealing with double and triple bonds. You're going to basically separate it out as if each of those bonds counted as one of the bonds to the atom over and over again until you reach your double or your triple bond. All right, so then number 4, now we're finally getting ready to assign R or S based on the fact that we have been able to rank our groups 1, 2, 3, and 4. So now, as we've been stating, you want to attempt to orient group 4 away from your viewpoint. So you want group 4 to be in that dashed position whenever possible. It's not always going to be given to you in the dashed position. So a tip for this is that if it is in the wedged position, okay, if group 4 is in the wedged position towards you, you can go ahead and assign the priority as R or S, but then you need to report the opposite priority back because it's the reverse of what you're seeing. So in other words, let's say that group 4 is out in front of me. I look at my 1, 2, and 3, and I say this looks like it's clockwise. Then that means that I would originally report it as R, but it's truly an S because I'm seeing the opposite of what I should be looking at for orientation purposes. All right, we have to have some standard, and the standard is that group 4 is placed in back, and we're looking at the top 3 priorities as if they were facing us. That's how we always assign R or S. And then finally, you're going to follow from 1 to 2 and then 2 to 3. So draw arrows. Go from 1 to 2. It doesn't matter if you cross over 4 or 3 in the process. And then you go from 2 to 3. And you follow that arrow from 1 to 2 and 2 to 3. And if the pattern is clockwise, it will be ranked as R. If it is counterclockwise, it will be ranked as S. And just an interesting note here, a lot of people get confused because they think, okay, R and clockwise, that makes sense because right-handedness and clockwise. And then they say, but what about S and counterclockwise? That doesn't make sense. And it actually comes from, it's kind of mean, but it actually comes from the term sinister because left-handed people used to have a superstition that left-handed people were evil, that they were sinister. And so that's where left-handedness and the counterclockwise basically terminology comes from, and it's stuck over the years. The S is in relation to the term sinister because left-handed people were considered evil, as mean as that sounds. All right, so if we apply all of this, let's take a look at some examples here, and we're going to attempt to rank these as R or S following the rules. So try to follow along with me here. I would encourage you to practice these if you can, and then if you get stuck or you're lost at some point along the way, you can go ahead and you can unpause the video. All right. Now, we're going to start off easy. We'll get a little more complex, and then in the practice, I will probably offer some even more complex examples as we get there. All right. So let's take a look at this here. Hydrogen, always a rank 4, and this is great because hydrogen is in back right now, so I don't need to worry about rearranging this molecule when I get to it. So bromine, chlorine, and fluorine, and this is a very typical example when you're first learning stereochemistry, okay, because the halogens are easily identifiable from one another, and you can rank them. So bromine is highest on the list because it would be furthest down on the periodic table. It would have the largest atomic number. So I rank this as 1, and I rank chlorine as 2, and I rank fluorine as 3. And I would go from 1 to 2 and 2 to 3, right? That's the way that I'm moving. So I ignore 4. Even if I were to cross over 4, if I had to do some maneuver like this, you ignore 4 provided it is in the back, which is, again, what we're hoping to deal with here. So if I look, this is going counterclockwise, right? Because I'm going from 1 to 2 over to the right here, and then 2 to 3. This is counterclockwise with the lowest group in the back, so this would be ranked as S. And I could draw its R enantiomer. The easiest way to draw the enantiomer is just to flip groups 4 and 1 with one another when it's set up in a positioning like this. So I could keep the fluorine here, right? And I could keep the chlorine. And then what I could do is I could say that this is now going to be the H, and this is going to be the Br. And now if I were to rank this, I would say here is 1, and here's 2, and here's 3. Now it looks like this is going to be S, but because the hydrogen has been brought in front, this is really going to be R in its ranking. And so that would be the enantiomer that I would have for the compound that I see over on the left there. And I could only draw an enantiomer because there is only one chiral center. I can't get a variety where I could do diastereomers in this case. All right, so moving along to this next one here. Now I've got a hydrogen, and the hydrogen is out in front this time. All right, so I'm going to rank this guy as 4. Now let's take a look at what I've got here. I've got an oxygen directly attached, I've got a carbon directly attached, and a carbon. So oxygen will outrank those others. I'm just going to delete what I put there to keep this neat as we're working on our ranking system. All right, now let's take a look. That methyl group at the top would be a carbon that has what groups attached to it? A hydrogen, and a hydrogen. So that's almost guaranteed to be lower in rank because it's all the lowest atomic number. The other carbon, which is a CH2, we're talking about this carbon right here that's directly attached, is going to be a carbon because it is attached to this other carbon right here, and a hydrogen, because don't forget that this is a CH2, right? There's a hydrogen and a hydrogen coming off of there. So if I were to rank this, what I would do is I would say this entire chunk is going to be rank 2, and this methyl is going to be group 3. All right? So how do I approach this? I go from 1 to 2, and I can cross 4, but I don't cross 3 until I'm ready. So I go from 1 to 2, and then I go from 2 to 3, right? So this looks like it's going counterclockwise. So I would rank this as S, but group 4 is in front, right? So because of 4 being in the front, this is the opposite of what I see, right? Because I want that in back. So what you're really saying is you look at this, and this molecule as it's set up would look like S, but then you would walk all the way behind the molecule, and then you're facing it from the opposite direction. So the true orientation of this is going to be R. That's the correct answer here. R is the orientation. And again, that's because the smallest group is in the front, so what I'm really seeing is the reverse image of how I should be assigning the orientation there. All right, so hopefully you guys are getting the hang of this. We've got some other ones we're going to take a look at here, okay, before we move on with our talk. I cannot encourage this state this strongly enough. I would encourage you to practice a lot of these types of problems. Go find old textbooks, look at other examples you can find online, practice stereochemistry until you're comfortable with it, okay? Because we have limited time, we can only do but so much in these coaching videos. So really try to soak in as much stereochemistry example as you can when you're preparing for this sort of stuff, especially because of the visual aspect. You can't really rely on math or on memorization too much for these types of problems. So when we get to this example here, I've got some clear-cut choices. This is for the nitrogen, because the other two are carbons, is going to be 1. Now see if you can follow along with my logic without drawing it all out here. I've got a CH2 and a CH2. Those are identical. This ends up in a CH3. I branch out here. I've got a CH2, and that third hydrogen that would have made this a CH3 is really bound to another carbon. So that means that this side that I'm circling is the higher ranking group, right? So I just did that without ranking and drawing this all out. Hopefully you could get to a state where you could do that. It would be important to save time as you're practicing. So this would be group 2, and this would be group 3, right? Now, group 4 is in back of us, so I can go ahead and assign based on what I see here, right? So here is 1 to 2, 2 to 3, and then back around to 1. Because this is in the proper orientation, meaning 4 is in back of us, I go ahead and I rank this as S without a problem here. All right, so let's move on to the next one that we have down here. This is the last example I have for this direct portion. Again, I will have an RS ranking question when we get to the practice session. So when I take a look at this one, all right, now I have a hydrogen. This one is in the plane. So this is going to be an interesting example here. I'm going to have to work on rearranging it. But let's do our ranking first. Okay, so this one's going to be 4 when I take a look at it. And then if I look at the others, I've got a carbon, because this is a CH2, and another carbon. All right, so I'm going to need to take a look at what's involved here. This carbon is bound to just hydrogens, the methyl group. So that's an easy rank 3 for me because it's hydrogen, hydrogen, hydrogen. This carbon right here involved with the OH group is going to be a C that has a hydrogen, another hydrogen because it's CH2, and an oxygen, right? So in this case, I would have this as the ranking. The other one that has the carbonyl would be oxygen, oxygen, and then carbon, not hydrogen, because it's attached to this carbon right here. There's no hydrogen directly attached to this carbon. So that clearly ranks the carbonyl as group 1, okay? And then the alcohol would be ranked as group 2. So this is going to be group 1, this would be group 2. So then I take a look here, all right? This is where it can get confusing. So I have to consider how this would look if I had the hydrogen in back. The easiest way that I can suggest this, and a lot of people will tell you, switch 2 of the groups and then change the orientation that you actually rank it as and things like that. I encourage you to use the visual skills that you have with this. Tetrahedral centers are like tripods, right? So I've got something that looks like this. Here are the feet of the tripod, and then this is the top of the tripod, all right? So imagine that I pick up that hydrogen and I just tilt it until it's in back of me, right? So I pick up the top of the tripod and I tilt it over. I want you to do that with me as you're walking through this video. Pick it up, okay? If you have a model kit, even better, and sort of lean it until it's facing in back of you. So what does that do? That takes what's in front of you right here and it brings it to the top, okay? Because if I took that top portion, what is directly in front of me, if I lean it down, is going to come up on top. Okay, what was dashed over here is going to be to the left, and what was already in the plane is going to be to the right. So hopefully you could see that. You can even imagine yourself if you slid and you basically were right underneath this molecule, you actually slid underneath of it. You would have up at the top at 12 o'clock, you would have that alcohol group. Over to your left would be the CH3, and over to the right would be the carbonyl, right? Now, if you have a technique that works better, then please, by all means, go ahead with that, all right? But this is the way I find it easiest, is just to visualize picking up the molecule and rearranging it. So at the top, at the 12 o'clock, would be the alcohol there, and then I have the methyl group over here, and then I have, this would be, I'm not going to draw the whole thing, but this would be where the carbonyl group is. So we said that this is rank 1, right? This would be rank 2, and this would be rank 3. Apparently all my examples came up as S when I was drawing them out. We'll try to make sure we get an R in somewhere. Okay, and then if I take a look at it, that would be counterclockwise, so this would be S, and that is the proper orientation considering that I just moved the lowest group, the hydrogen, to the back. So the hydrogen would be hanging out in back here, right? And then if I were to pick it up and set it back down with the hydrogen on top in the plane again, it would be the same molecule, if you can visualize that or see that. So what if I didn't do that, right? What if I just said, okay, based on what I have here, this is group 1, and then I go to group 2, and then I go to group 3, and then I come around to group 1 again. That would look as though it was R. Okay, so what you can do is you can switch these, and if you turn around and you say, I'm going to put 3 in place of 4, right? You have to, when you do that, okay, so you draw it out here. So you say, I'm going to put group 3 here, which is CH3, and then group 4 back here, which is the hydrogen. And then over here, I'm going to keep the carbonyl portionality, right? So how would this work? I would have 1, and I would have 2, and then I would have 3. So if I look at this, this is going clockwise. So you still have to be careful because this looks like R, right? If you were to do this. And so you can't, it's usually not as easy as just picking any 2 groups and switching them. You really have to know which groups you're picking in order to visualize this properly, and then you can move on with it. All right? So whatever technique you find works for you, that's what I would encourage. I usually use visual techniques, and I tell my students to attempt to use visual techniques, spend time with models, but that's how you rank R or S based on the various rules that we have here. So we're going to briefly bring up some meso compounds to look at that. I will discuss the importance of stereochemistry in drug design and plain polarized light. We're not going to really look at calculations or anything with that. And then we will get on with our practice so that you can implement some of this. All right, so that is how you rank R or S. I'm going to clear the board and we'll briefly talk about meso compounds. Okay, so now that I've cleared the board and I've brought up this new material here, I just want to remind everybody where we are as far as covering stuff. So if you take a look, we've covered the rest of this. We're now up to meso compounds, which we're going to discuss here. We mentioned them earlier in the video, sort of in passing briefly, but we're going to come back to that now and look at identifying meso compounds for a minute or two. And then the last 2 are really going to be more discussion type of things. So I have a few bullet points that I've put up that we will discuss, but it's very important to understand the theory behind stereochemistry. And so we'll discuss those last 2 items before we break into a practice session and then finally a summary and review. So we're almost there. All right. Meso compounds. So what we discussed earlier is that when you're dealing with chirality, you have individual carbons that can be called chiral centers, and then you can have chirality of an overall molecule or compound. And so when you get ready to deal with that, if you have a compound, you have to remember it could potentially have chiral carbons. However, the overall molecule is achiral if there is a plane of symmetry. And so that is what we would refer to as a meso compound. Now, meso compounds, while they have the chiral centers, they are achiral as a compound overall, and that means that they will not behave as regular chiral compounds do. So in other words, the chirality centers within a meso compound have a plane of symmetry, and therefore they cancel one another out as far as optical activity with plain polarized light is concerned, or things of that nature. So how can you identify symmetry within a molecule? You usually can pick it up just visually if you're looking at it, but the real goal here is that you need to be able to analyze the molecule 3-dimensionally and see if you could draw a plane of symmetry through it. Now, for some people, this is a little bit easier than others. For instance, if you take a look at the 1,2-dimethylcyclohexane here, I can find a plane of symmetry that comes and cuts right through the center of the molecule here. All right. Now, planes of symmetry, you can see this one. This is almost as if you were to imagine looking at the molecule from above and you're drawing the plane of symmetry going through. Sometimes if you have, for instance, chained compounds, right, so like a carbon chain, you need to imagine a plane that can slice directly through that chain, or basically within the plane of your vision. All right, but anytime that you can draw a plane of symmetry and almost fold a mirror image on top of itself within the plane of symmetry. So imagine if I took this six-membered ring, and where I drew that orange dotted plane of symmetry, I sort of just folded the compound up, okay? In that case, I would have a mirror image for the compound. Now, as you're doing this, you need to realize that sometimes it can be a little bit trickier. So sometimes you may have trans compounds that look like they might not have a plane of symmetry, but they do, especially for six-membered rings, because you have a chair conformation, right? So if I can run any type of plane of symmetry through and I can get an identical version on one side of the plane and the other, then it would be considered a meso compound. So another example, hopefully this one is pretty obvious from the one up above. If I take a look at this diol compound, I can easily draw a plane of symmetry. Hang on a second, let's straighten that up some. Right through here. Right? So if I were to fold this in half along that plane, then that plane of symmetry would show that this is a meso compound. And so I do have these individual carbons right here. I could try to designate them as chiral, right? Because I could say, well, I have an alcohol. I would also have an implied hydrogen that I'm going to find right here out in front. And then if I go around the ring, I have a CH2, a CH2, but then I have a C with an OH, and here I have a CH2. So I do come to a differing point. So a lot of students, they look at this and they think, oh, I've got a chiral compound. You have specific stereogenic centers that you could label 1 through 4 for the substituents and try to rank R or S. But overall, the compound is going to be a chiral. And then finally, you can take a look here that we would have a plane of symmetry that you could really draw directly through if you were to slice this. So imagine that I'm really drawing the plane of symmetry going straight down the middle of the molecule here, right? I would be able to find a plane of symmetry if I was working with it like that. And so, again, whenever you have a plane of symmetry that you can work with, you're going to have an achiral compound. Now, some people can see when you're working with this that you could also draw something this way, right? However you find is the easiest method for you to determine if there's a plane of symmetry, that's what you want to focus on. But it will be important that you can differentiate if you're working with a meso compound versus a compound that is going to be chiral. All right, so that really takes care of discussing meso compounds. You're looking for planes of symmetry within the molecule itself. Now, a little discussion as far as plane polarized light. And you may remember a lot of students discuss this, but they don't really do calculations. There are things such as enantiomeric excess and where you can actually calculate how much rotation of light is expected if you have a basis to start with. But that's not something that we're going to be looking at here. We're just going to discuss the idea of plane polarized light, all right? And clear up a little bit of confusion because sometimes students get confused here. Chiral compounds, so not meso compounds, but going back and talking about if a compound overall is actually chiral, it will have the ability to rotate plane polarized light. So if you take light and you polarize it on a specific plane, you will have, if you have a chiral compound, the ability to rotate that light one way or the other. And the direction that the light rotates is going to be based on which enantiomer or which stereoisomer you currently have or is present. Okay, now here's where a lot of students tend to get confused. R and S, the designations we've been working with, have nothing to do with the direction in which the light will be rotated, but it will rotate in opposite directions. So in other words, R and S will rotate light in equal and opposite directions of one another. However, a lot of students think that, for instance, a given compound, let's say that a compound will rotate light 5 degrees, okay? And we talk about degrees because if we're looking at light, you usually view it through a polarimeter, and then you can adjust, sort of like a compass, the number of degrees that the light is actually going to be rotated. Now, let's say that a specific compound can rotate light 5 degrees. A lot of students have a misconception that R will always rotate light plus 5 degrees to the right, and that S will always rotate it minus 5 degrees to the left, so counterclockwise. And it makes sense if you think about this. for a second, because a lot of students are taught that when we do the stereochemistry designations with the rules, that whenever we have the clockwise, the right-handedness, that is going to be R. And so then they translate that to R must always rotate light clockwise to some degree, and then S must rotate it counterclockwise to some degree. And that is not true. So again, we mentioned the idea of D and L, which tends to be more of a biochemistry term, but it's still referring to which way light is rotated when we're talking about D and L. So sometimes you could have light that is being rotated to the right or clockwise for the S enantiomer of a compound. It is completely possible that you get the opposite effect of what you're going to think, and that's something known as absolute configuration. So does the R or the S enantiomer of a given set of compounds rotate light in the D direction or in the L direction based on a biochemical type of analysis? And so you have to keep in mind that the R or the S, the only way you're going to find out which direction it rotates light in is to put it into a polarimeter and actually do that experiment and determine it. Because it could turn out that the S rotates it in a positive direction, the R rotates it in a negative direction. Now, what you can be sure of is that if you were to measure the pure enantiomer, meaning either you pick the R or the S, if you measure the pure enantiomer for one of them, the opposite enantiomer will rotate the light in equal and opposite directions. So let's say that I analyze some sort of drug or compound and it has the R configuration associated with it. And then we find that that rotates light to the left. So it would be designated as L as far as its rotation of light is concerned. All right, that would mean that the R in that case is going to be associated with a negative, some degree amount. We'll just put a random XX here, but that the R is negative. So that would mean the S enantiomer must, if it's pure, rotate it in the positive opposite direction, an equal amount, whatever XX is. Let's say 3.5 degrees or something like that. All right. So what's important here? Two takeaways. R and S have nothing to do with the direction that the light will be rotated. You determine that experimentally. That's point one. Point two is that the light will be rotated in opposite directions by each enantiomer to an equal and opposite degree. So then sometimes you may have, let's say, 70% of the R and 30% of the S. You can do calculations if you know the pure optical rotation of one of them, okay, to determine how much that S is going to affect it, right? Because the S would counterbalance part of the R, and then the leftover remaining portion of the R would be what's able to rotate the light. So I wouldn't expect it to be able to rotate it to as large a degree as if it was just the pure R enantiomer. So hopefully that makes sense. We really want to just talk about this conceptually. All right, now meso compounds, because we were just discussing those, and racemic mixtures. So this term, racemic mixture, is going to be if you have a mixture that is 50-50, so 50% one enantiomer and 50% the other. So in other words, 50% R and 50% S. Both of these, meso compounds and racemic mixtures, will not rotate plane polarized light. All right, now the racemic mixture hopefully makes sense as far as what's going on there. So if R and S have the capability to rotate light in equal and opposite directions, and I say, let's make a solution where 50% is R and 50% is S, and let's see how it works in the polarimeter, you're going to get a complete canceling, right? Because for every R molecule rotating at 1 degree, you're going to have the S molecule rotating at the equal and opposite degree. And so true 100% racemic mixtures where you have a 50-50 split, you're going to not see any plane polarized light activity. Now the same is true for a meso compound, because if you go back up and you look at your meso compounds, in a meso compound you have this, it's basically a racemic mixture almost that's built into the molecule. So in other words, if I were to classify this, one of these would be R, right? One of them is going to rotate one way, and then the other is going to rotate the other way. And so in this plane of symmetry here, I get an internal canceling of the rotation of light. And that's why when we deal with the meso compounds that are achiral, they also will not rotate plane polarized light, because the compound itself has a canceling effect, when you take a look at it. Now, let's talk about purification, because a lot of times chemists create these drugs for pharmaceutical purposes, and obviously that plays a direct impact. If a lot of you are looking at doing MCAT and going to med school, you potentially will be prescribing drugs to patients, and you want to have an understanding, or at least an appreciation, for stereochemistry and how that plays an effect with the human body. And we're going to talk about a brief case study here as we discuss this. So, the FDA and the other regulatory processes that we have set up here in the U.S., or in most countries for that matter, are going to heavily regulate the production of these various compounds, especially before they hit market. One of the things that you will need to test is whether or not, if you have a drug that has a chiral center, whether or not the enantiomers are going to behave the same way in the body, whether one of them will be active, the other will be inactive, or hopefully the result you're not going to be obtaining, right, is that one of them is active and the other one is detrimental. And we'll again talk about a case study where that happened. Now, one of the problems with dealing with this sort of regulatory process is that purification of stereoisomers is extremely difficult, and I'm going to emphasize that here. This is a very difficult process. Now, the reason for this is that a stereoisomer is only going to differ in the way it's organized three-dimensionally in space. So it's going to have the same functional groups, it's going to have most of the same sort of structural properties, except that it's a mirror image when we're looking at the chirality centers, the non-superimposability. And so what that leads to is a complete mirroring of the chemical and physical properties, right? So if I look at, for instance, a chiral center that has a hydroxyl group, okay, in one case the hydroxyl group might be on one side of the plane, and in the other case it's on the other side of the plane, but that doesn't change the fact that this compound will undergo hydrogen bonding to the same degree. It doesn't change the fact that it's going to have the same melting point. It doesn't change the flammability of one enantiomer versus another. They're going to have the same chemical and physical properties. And this is one of the big challenges that face chemists that are creating compounds that they would potentially like to research for drug design or therapeutic effects, is that when you're dealing with enantiomers, the body is sensitive to enantiomers, and you cannot just toss in a racemic mixture and hope for the best, because that can cause serious problems. So one of the ways that we can isolate these, and it's very difficult, is you can use enzymes or other sorts of derivatives that you would find from living systems that can selectively bind to one enantiomer versus another. So one of the things that's interesting with the human body and with most living organisms is that there are selective binding sites for one enantiomer versus another. And so many times, it's almost like when you've heard the term lock and key model or things like that, you've got a perfect fit for one enantiomer to one specific binding site. And a lot of times the other enantiomer is not going to fit that lock and key model, because what you're dealing with is the mirror image, and so it's just like a glove for a specific hand. If it fits, it's a perfect binding fit, but otherwise it's not going to properly fit on that hand, right? Well, the same thing is true for chiral compounds in the body. Now, that could be a problem, or it may not be a problem, because when you deal with this, if the compound that does not fit the lock and key model goes off and simply sort of gets degraded or breaks down in the body and has a reasonable half-life, doesn't build up any toxic effects, that's not really a problem, right? We'll excrete it out, the liver, the kidneys, the urine, all that kind of stuff. We can sort of process these undesired side compounds and get rid of them. But it can be a serious problem if the other compound, the other enantiomer that does not fit that lock and key model, finds another area that it can lock and key or bind to competitively and interfere with some sort of bodily process that could be detrimental or cause harm. And so that is one of the big challenges, is how do we purify these? A lot of times chemists, when they're working with this, they need to find enzymes or other types of biologically active solutions that can selectively bind to one and then remove it. Now, one of the other problems that chemists can face or come across is that when they are working with this type of purification, many times compounds will have the ability to what's called racemize, or go back to a racemic mixture within solution. So in other words, you take the pure compound, and then in the body, let's say that you have an acidic proton at one of the chiral centers. Well, when it enters the stomach, the acidic proton could potentially be removed and then added back on, and you can very easily change through chemical reactions the designation, whether it be R or S, in that specific chiral center. So it depends on whether the group is exchangeable or can sort of undergo this racemic process, depending on how it's going to be treated in a living system. Now, again, this can be very expensive for drug design when you get ready to do chiral purification, and that is one of the long-term, sort of drawn-out parts of this process when we start talking about bringing a drug to market, start to finish. The average time span, now I haven't checked this in years, but the average time span back when I was in graduate school was about 20 years. It's 15 to 20 years to take a successful drug from the beginning, meaning you're proposing it, you're actually starting to synthesize it in the lab, up through all the proper trials before it can sort of get released as a beta testing drug, before it really officially floods the market or things like that. And you have to go through and you have to test and track how each of these enantiomers are going to break down in the body, because that's a very big thing. Now, if you show through trials that you can successfully administer your drug as a racemic mixture and that the other one does not have any adverse effects, it obviously is going to make the drug much cheaper and more plausible for a pharmaceutical industry to pick up and mass produce than if you were to say, well, only one enantiomer works and you have to go through the painstaking process of removing one versus the other. That can really sort of bring question as to, is this going to be a plausible drug candidate? And if it is, how expensive is it going to be? Because that could really increase the price for patients that are the end users of these drugs. All right, so a case that probably a lot of people have heard of, it's very common for organic chemists when they're teaching their undergraduate classes to use this as a case study, but I'm just going to mention it here, is thalidomide. All right, now thalidomide was a drug that was used in the late 50s and the early 60s. It was administered for morning sickness. So when women would come in and complain and they would say, I'm having, very bad morning sickness in the first trimester, thalidomide was basically given as a mild sedative to help sort of reduce some of that and provide some relief to these women who were pregnant. Well, the problem was it was never tested as far as the enantiomers, and it turned out that the R enantiomer of thalidomide was binding and doing its proper job as far as the therapeutic effects. However, the S enantiomer was not providing that, and instead of just being regularly broken down and flushed out of the system, it would latch on to specific binding sites for the embryo or the fetus, and it caused severe deformities. So what happened was, after this drug was administered for a while, all of a sudden we started seeing these huge waves of children that were being born without limbs, or they were having, extra sort of deformities with certain extremities. And this became a serious problem because for the company that was manufacturing thalidomide and the people who went through this process, they realized that it was one enantiomer versus another that was responsible for this. And if it had been sorted out and they had been removed into sort of the two separate camps, they would have realized that one causes these issues and the other does not. So that sort of spawned a whole thing in the mid-60s and the 70s where there were huge regulations that came down from the government that stated, we're going to need to start looking at how we can separate these out and test for them individually before we're just basically giving these racemic cocktails to people and saying, oh, don't worry about it as long as it's providing the desired effect. And so that is sort of some of the background or the history as to where this comes from, and also why it's so important. So why is stereochemistry so important Well, one of the big reasons is that biological systems are sensitive to specific chirality and specific orientation. And so your binding site is going to pick up one versus the other when you're looking at that. So that really wraps up the discussion of why it's important in drug design and a little bit of the discussion on plane polarized light, which I really just wanted to introduce and remind you about here. All right, so what I'm going to do here, since we've covered everything, is I will clear the board, and then I will bring up some practice questions in related to stereochemistry, and then we will finally do our summary. So let me clear the board, and I will be right back. Okay, so what I have brought up here are the questions for the stereochemistry lecture, and we'll go through these together. Again, as always, you should attempt to answer these yourself, and then unpause it and work through the walkthrough when you feel that you're at that point. So number one, which of the following would be given the highest ranking priority at a chiral center? So imagine that all of these are stemming off from a carbon that we would consider chiral, because these are all 4 different groups. Which one of these would you rank as number 1, the highest priority? So you can see the different options there. You have a cyano or a nitrile group. You've got an amide, you've got an amine, and you have an alcohol. So they all start with a carbon. You will need to determine which of those carbons is going to be ranked as 1 based on the other material that is bound to that carbon. Now, number 2, the following compounds are best described as. You may be able to just do this visually, and I would encourage you to if you can. But there are 2 sets of compounds there, and you are going to describe them as either diastereomers, enantiomers, meso, or the same compound. So those are the choices. Right, number 3, the following compound has what orientation? And you can see you've got 2R, 3S, 2R, 3R, so on and so forth, through all the different possibilities. Now keep in mind, position 2 is the alcohol, position 3 is the chlorine when we're referring to this. So that numbering is really following the ranking of the substituents that would be present there as far as naming or IUPAC standards. All right, so then number 4, how many stereoisomers can the following molecule have? So you've got that molecule, let's say that that was some sort of drug candidate or something like that. How many potential stereoisomers might you be dealing with if this was your compound of interest? So that's going to depend on the number of chiral centers that would be present in that molecule. All right, and number 5, a little bit more of a theoretical question here. Which of the following statements is incorrect? And you can read through those and you can decide which one would be incorrect out of the bunch. So, those are the questions. I will scroll through them slowly one more time in case you need to copy anything down. And then again, I would suggest that everybody pause the lecture series, attempt to do this yourself, and then once you are confident that you're ready to look at your answers or you're really stuck and you need help, at that point, why don't you go ahead and you can go through the walkthrough. All right, so I will see everybody in just a minute when you unpause the video and we will go through this together. All right, so hopefully everybody had a chance to work on these questions. So let's get started as far as what the answers are here. So for number 1, which of the following would be given the highest ranking priority at a chiral center? So let's take a look at these. They all come from a carbon, so it's going to depend on what the carbon is bonded to. In the case of cyano, we really have a triple bond like this when we deal with nitriles. So it would be N, and then remember the triple bonds get counted each time that you repeat the bond. So as far as ranking is concerned, this would be 3 nitrogens. Right? Now, the next carbon, which would be the amide in selection B, is going to be oxygen, oxygen, nitrogen. And that's because the amide would look like this. So I've got 1 to the nitrogen and then a double to the oxygen there. Right? The following amine would be a hydrogen to that carbon, a hydrogen, and then the nitrogen that is the actual amine portionality. And then finally for D we would have a hydrogen, and an oxygen for the alcohol. So the correct answer here as far as your ranking, it would be B. And that is because we take it based on the atomic numbers of the atoms involved. So if it's all going to start with carbon, then we look at the direct attached atoms, and those atoms, we basically sum up and rank all of their atomic numbers. Oxygen being the highest out of this collection, we have nitrogens, oxygens, and hydrogens. So 2 oxygens and a nitrogen, that's going to be the highest ranking of the bunch. So this would get ranked as 1, and then you would follow suit and say the cyano is 2, so on and so forth, using these rules. All right, number 2. The following compounds are best described as. Now hopefully, because one of your goals here is to save time when you're working on the MCAT, you were able to analyze this without going through and assigning R or S at every potential chiral center. Now, how would you analyze this? Well, you would say the chiral centers are any place that I have a hydroxyl, because the hydroxyls have the OH, they have an implied H on the opposite side, and then they have whatever's over to the left or the right. So for instance, this first hydroxyl would have a methyl, and then this whole clustered hydroxyl group, the diol group, that's over to the right. And you could do this in each of these cases, right? Now, you have to be careful. Some people might go to identify this center as being achiral, and that's not the case, because you have a methyl over here, but you have an ethyl over here, and that's going to be a big driving factor in this as to why there's not going to be meso and why that is technically a chiral center in the middle. All right, so we don't have a plane of symmetry because this molecule itself is not symmetrical. So I don't need to worry about which way are the groups oriented with the hydroxyls, because I can already look at the chain and the placement and say, well, if I have a methyl on the left and an ethyl on the right, that's going to ruin the symmetry that I would be looking at, and therefore I'm not going to consider this to be meso. All right? Now, when you take a look at the remaining, because these are each going to be considered a chiral center when I'm working with them, I can simply look and say, well, 2 of these have remained the same, this one and this one, whereas this one has changed. And so if at least one changes but not all of them have changed, that's the definition of a diastereomer. And that is what I would be looking at here, is a diastereomer. So enantiomers and same compound would be out. The enantiomer would require a change at every chiral center, and then the same compound would mean that these need to be exactly what it says, the same compound. So all of the R's and S's would have to line up, and they don't. So that would be the answer for 2. All right, number 3, the following compound has what orientation? So if we take a look at this, you've got 2R, 3S, 2R, 3R, and it goes through and it lists all of these. So let's just get straight in. This time, assigning priority is the best way. So for position 2 here, I'm going to put that the hydroxyl would be rank 1, and then rank 2 is going to be this entire alkyl portionality with the chloro right there. So that's going to be 2, and then the methyl over here would be 3. So if I take a look at this, okay, then the hydrogen would be implied in the back here. And so that is going to lead to the proper orientation, the way it should be facing. Group 4 is in the back, and it would go 1 to 2 to 3. So this right here would be clockwise. And I would associate number 2, which is the hydroxyl group, as R. All right? Now, that means that I've already eliminated 2 choices. C and D are now out. So all I have to do is find out what the chloro orientation is going to be, and then I should be good to go. So let's change colors here. So for this particular chiral center, the chlorine is going to be rank 1. Okay? And then similar to the hydroxyl, it's going to be the portionality with the hydroxyl group. So this chunk right here, which is going to be part 2, and then this methyl off to the side, which is going to be 3. So there's the general order. All right, so it goes 1 to 2, and 2 to 3, and then back around. Now, one of the important parts here, okay, I'll redraw this because it's not as evident with all my chicken scratch there. The chlorine is facing this way, which means the hydrogen is facing this way, right? So if this looks like it's rotating clockwise, which is R, keep in mind group 4 is in the front, we're really seeing the opposite of what we're expecting. So that means instead of it being 3R, it should be 3S because this group is out front here. So 2R, 3S, selection A, is going to be the correct choice when you are working with this problem. All right, 4. How many stereoisomers can the following molecule have? Well, let's take a look here. You have to be good at locating chiral centers in order to do this. So anything that is a CH2 or a CH3, meaning a methyl, will be out of the running. So let's go through and eliminate those in the first place. So this would be out, this would be out, this would be out, okay, this would be out, this would be out, this would be out. So just keep in mind here when I'm discussing this, I don't need to analyze whether something is R or S. I simply need to analyze how many actual chiral centers I can come up with here. All right. Now, if I take a look at this, I have to look at the number of areas now. So let's look at what's left. Would this potentially be a chiral center? The answer there is no, because I have a double bond. So double bonds ruin the whole idea of having 4 groups that are unique from one another. What about this one down here? Well, there's a hydrogen in back here. So yes, this one would count as one. So far I've got 1 potential. What about this one up here, right? Well, that would have a hydrogen out in front. And that would be 4 different groups because this ring is not symmetrical. So that would be another one. So add another to the tally marker. Okay, now this hydroxyl group here, this carbon would also be 1 because you have hydroxyl hydrogen and this ring is not symmetrical. The left side of it has this other larger ring group coming off. So that's another one that we can tally up. Right? And then if you take a look at this carbon right here, right? This carbon is going to be a chiral center as well. Now what you have to look at here is that because this one, right, is directly attached to this one, whether this is dashed or wedged is going to affect how the other one is. And so you basically, these two are linked to one another. You can't escape the fact that these are both linked together. And so this really behaves as one single one because this is a little bit tricky. I wanted to put this one in here. If I changed the orientation of the carbon right here, it's going to directly change the orientation of this group right here. And so if I take a look at that, I could sum that there are going to be 3 total because that last one, they interact together. Okay, and therefore the rule is 2 to the n, where n is the number, and we're going to utilize 3 in this case for a total of 8 as the possibility. All right, now which of the following statements is incorrect? So let's analyze these one at a time. R enantiomers will always rotate light clockwise. Is that true or is that false? Well, that would be considered false. So this is definitely a selection, okay? Because we discussed that R enantiomers will rotate the equal and opposite as far as light to the S enantiomer, but we cannot directly predict whether an R enantiomer is going to rotate light clockwise or counterclockwise. The clockwise sort of term that we use with R is simply for assigning its stereochemical designation. It's not referring to which way it's going to rotate light. Now, when we take a look at B, running multiple fractional distillations is a good way to separate enantiomers. Well, that would really not be an appropriate choice here because running multiple fractional distillations is considered to be separating through boiling point. And we've discussed the fact that enantiomers are not going to be easily separated through physical properties, and boiling point is a physical property. So that means B is also incorrect. So you're already aware now that D is the one you're going to be going for, right? But let's just check here. If an enantiomer of a drug is separated and is shown not to cause side effects, the other enantiomer need not be tested, provided the one that is tested is the one that's brought to market. Well, in that case, that would also be false. And that's because when we discussed the importance of drug design, we said that you could have racemic mixtures that are going to basically, once you isolate one, it can racemize and go back into a 50-50 mix depending on the conditions in the body. So just because you separate out one and you do not find that it causes any problems does not mean that you can then go ahead and administer that one and not test the other, because there is a chance that once you administer it in the body, you could have this racemic mixture behavior coming back, and then you could potentially be exposing the person taking the drug to that other enantiomer. All right, so that covers the questions, and we will now go ahead and take a look at the summary. So let me clear the board and we will summarize what we've learned here with stereochemistry. All right, so here is a summary of everything that we just learned in this fairly comprehensive lecture. So we first discussed chirality, and the idea of chirality being molecules that are non-superimposable with one another. And when we discussed this, we gave examples where we were dragging our hands over top of one another, provided the palm, either face up or down, was the same way for each hand. And we sort of did some talk about mirror images as we were holding our hands up. So chirality is when we're dealing with non-superimposable molecules, or at least sections of those molecules that are non-superimposable. Now, chiral centers, okay, because an overall molecule could be chiral, we determine that as to whether there are stereocenters or chiral centers, and this is a carbon that has 4 different groups. Now remember, we're mainly focused on carbon because it's the most prevalent in organic systems, whether they be living or whether we're talking about drugs or things of that nature. There are several different classifications that we discussed. Enantiomers is when we have a differing at every single chiral center. So that means all of the orientations have changed, and it is a perfect non-superimposable molecule when you're looking at 2 sets of enantiomers. We then discussed diastereomers, which are the other parts of the stereoisomer family, and they differ at 1 or more, but not at all, because if they differed at every single stereocenter, they would then be classified as enantiomers, but they have to at least differ at 1 stereocenter. Otherwise, if they're all the same, it would be considered the same molecule. And remember that we used the formula 2n, where n is the number of stereoisomers that are, the number of chiral centers. That will find you the number of potential stereoisomers. Just a note about this formula, you also have to be careful with meso compounds, because meso compounds can appear or present to have 2 different forms, like enantiomers, and they would really be the same compound in that case because of the achirality of the molecule. All right, so speaking of meso compounds are achiral compounds that contain a plane of symmetry. And when we talked about racemic mixtures, specifically with plane polarized light, or drug design, racemic mixtures is simply referring to a mixture of 2 enantiomers in a perfectly equal ratio. So it's a 50-50 mix of those enantiomers. Now, the main focus here, we were discussing R or S designation based on the ranking rules. So in order to do that, we had to orient the various groups in order to put group 4 away from us or in back, and then assign the designation. And that was using the varying combination of rules where we said, here's this atom, and then based on the atomic numbering of any atoms involved, we're going to give the highest ranking atomic number rank 1, and then we decrease from there. So we could determine R and S classification. However, we noted that R and S classification do not specify light rotation. So in other words, R does not always rotate light to the right, and S does not always rotate it to the left. It could have to be determined experimentally, and once you've done that, you could then assign what's called the absolute configuration. What we do know is that the R and the S molecules will rotate light in equal and opposite directions if you're dealing with the pure enantiomer solutions of one another. And you can use something called a polarimeter in order to determine that. It's very difficult to separate stereoisomers, and this is due to the fact that they have shared physical and chemical properties. So again, boiling points, melting points, solubility, all of these types of things are not going to be useful when you're attempting to separate stereoisomers that have chirality like this. Most of the time, you need to bring in some sort of derivative from a living system like an enzyme or a binding site that will specifically pick up one of your enantiomers and leave the other one alone. And then whether you take the bound enantiomer and remove it, or whether you're interested in the enantiomer that was not bound, that's a way that you can attempt to separate them from one another. Now, living systems have chiral sensitive binding sites. That's one of the whole issues with needing to separate these compounds most of the time, is that if you're interested in administering any type of compound to a living system, primarily humans is what we deal with, especially in medicine, but living systems have sensitive binding sites. They're going to be like a lock and key model where they will pick up one of these enantiomers and not the other. And that can or may not have detrimental effects. It's going to depend. So you need to do your proper homework and separate these out ahead of time before you were to bring it to market. Okay? And again, I have a note there that separating enantiomers is a part of the drug design process, and that is so important because you cannot have detrimental effects if you're basically administering these racemic mixtures to people when you're giving them drugs. So that covers what we really wanted to discuss for chirality and stereoisomers. So hopefully everybody has had their questions answered based on this content. So thank you for learning with the MCAT A series, and we will see you guys for future lectures.